Morning. So on the board, we have a question with the area calculation within the worker. Formula is will be done in five. Area within a worker is A equal to 1/2 integration R squared d theta. So for example, the R equal to 4 plus cosine theta. So we will calculate 1/2 integration 4 plus cosine theta in theta. when you start out trying to calculate this, you normally have to determine the integration limit. In this question, the limit is already given 0 to 2 pi. That's, oh, there's R squared. Remember to check your integration limit if it's not specified. For example, in this question for R equal to 4 cosine theta plus cosine theta. You can see that when theta equal to 0, then this is a 4 plus 1, which is 5. It's at angle 0. And when theta equal to 90 degree, pi over 2, cosine 90 degree is 0. So at 90 degree, going to 4 plus 4. So that's 0, 4, basically. The 90 degree R 4. And then we theta equal to a little bit there. We theta equal to pi, cosine pi is -1. So 4 plus -1 is 3. So the distance is 3, but it's distance is 180 degree at angle, but then the distance is 3. That's 3. Right, so you can see if you try to sketch the graph, it will look like this. Then at 3 pi over 2, cosine 3 pi over 2 is 0, so we have a 4. Right, and 2 pi cosine 2 pi is 5, so we back it. So you can see the whole thing. It's a closed curve once we reach back to 2 pi, which is a reason that pi is a well-defined. Right. That's right. Okay, so let me write out the calculation. I have this here now, if you are not. We calculate the area. It's equal to 1/2 R squared d theta. Integration R squared d theta to 2 pi R squared is sine theta squared. So this is 1/2 integration of R squared d theta. And in order to finish the calculation, we can leave the integration limit alone and just work on the in-depth integral. We finish the square calculation, right? So square calculated at 4 squared 16 plus 4 times cosine times 2 is 8 cosine theta. We're expanding the calculation of the square. The last one is cosine squared theta. So that's the integration question. And we still won't be able to integrate it because this part still have to be reduced. So we have to write it into a form that's possible to integrate. So let's carry, so make it easy. Copy. So many of the terms we have to carry, except the cosine squared theta. So we would apply double angle formula. The cosine squared theta equal to 1/2 plus 1/2 plus 1/2 cosine double angle. Space. So cosine theta becomes cosine 2 theta. But at least the degree is reduced instead of power 2. Now it's all power 1, and we're ready to integrate. So then let's see, there's 1/2 if you integrate 16. The variable is theta, so 16 has to enter 16 theta. Plus the antiderivative for cosine is sine, so it's 8 sine theta. That's the integral. And then the 1/2 if you integrate is 1/2 theta. And then the 1/2 cosine 2 theta. So 1/2 you keep it, cosine 2 theta integrated is sine 2 theta over 2 because of change. Right? So that's the whole antiderivative. So integration is done. We still have to put in the integration limit. It was, I didn't write it because I felt like we don't need it to do the calculation. And now we have our antiderivative. Now we're doing the calculation of the definite interval. So we put in the 2 pi and 0, realize sine 2 pi equal to 0, sine 4 pi also equal to 0. So all those signs will only provide 0 value. So only the one that has theta activates this one. See. I hope that you already have your answer down. Thank you. You haven't finished yet. I'll go back and finish this. That's okay. So after we've done here, is mostly done since we already have a formula. So continue from the left is 1/2 and 16 times 2 pi. But remember that was 0. Sine 2 pi equal to 0, sine 0 equal to 0. That is also 0. The only thing that's non-zero left is plus 1/2 times theta, and theta is 2 pi. So plus 1/2 times 2 pi. Right, so that's the value of the definite or the value of the area. And of course you would simplify it. So it's 1/2. That's 32 pi. So this is 1/2 times 2 pi, which is pi. So it's 32 pi plus pi. Okay. And then that's 32 pi plus pi is 33 pi. So it's 1/2 33 pi. If you combine the number is 33 over 2 pi. So that's the whole process of everything. So let's go back to the page. So I can report. So this is an example on the area calculation. I think I recorded all your answers. Eduardo, are you still working on it?
I got it.
Yeah. But, okay, that's right. Anyone else? Let me see how many of us are attending online. Anyone of you don't have your link yet? I think I see everyone's. Okay, so the answer is 33 over 2 pi. And this is an example on calculating the area within polar curve. Do you have any questions? Any homework question? As you all know, we finished our chapter 9 only with section 2, 3, 4, 5. Did you submit yours already? Okay. So we should be getting ready or try to prepare for the last test, last in-semester test. So the test we still have is test 4, which we schedule for next Thursday, and the final exam. Our final exam, I think, is May 6th. We talked about the schedule before, yes? Okay, so let's see, and just to make sure that we plan ahead, so everything is announced. The final exam, I think I put it on the scheduling. Last week, last day of class is May 4th. But after that, we don't have official classes, but kind of put the schedule there. May 6th, Wednesday, it was a Wednesday, between 10:15, 12:15, that's our final exam time. May 6th is the first day of all final exams. The final exam week lasted this May 6th to May 12th. So you may have other dates for your exam, but that was maybe your first exam in that way. First final exam. So let's try to make sure that we put that on the calendar. Other than that, the rest of the time, we have a test on the 23rd. The rest of the time, we'll try to get ready, either get ready for the test or get ready for the final exam. As we were waiting on getting preparation on those, we're probably gonna go over a little bit chapter 10. Normally, I would cover 10.1, 10.2, 10.3, 10.4, so that was planned. There are 6 sections in chapter 10. But normally I don't finish the whole chapter. I just start it a little. Any questions? Yes.
So chapter 10 is not gonna be on the one.
Let me see. I felt like it could be on the final, it could, but it's definitely not on test 4. What is on the final or not? I want to see if what I did do last time. There's a plan. All right, so then the original plan was to have 10 questions on the final exam. The first question is integration by part, which you can study 6.1. The second question is trivial integration, which will be what we did in 6.3. There's in partial fraction decomposition 6.4, calculation volume 7.2 or 7.3, calculation of surface area, which is 7.4. Infinite sum, that was A2, A3. Taylor series is A7 or A8. Equation of tangent line, which equation? So based on this, we don't have any chapter 10 on that, but we have homework. Other than the homework from chapter 10, as we were studying, we won't have any major question on the final or on the test. So that's the plan, at least. Any questions?
You still get a note card like we've been able to have.
Yes, you still get a note card for, and also if you do have all your chapter 10 homework finished, you can bring that for extra credit on final exam. So it's kind of like the regular plan. I'm still hoping more students will do the homework and write down the calculation, write down your ideas, because the more you write, I feel like the writing part improve our understanding. So the more you think about it, the more you write, the better it will become. And also, the more you write, I don't know about you, I like to organize things. Okay, maybe the problem, the first time you solve it, you may have a lot of writing, some of them make sense, some does not. But as you do more questions, you make it more concise and you make it more organized. So then the writing is part of the organizing our mind, organizing our method thought process. So it's should be helpful, I think. And so anyway, it's people learn differently. To me, I feel like writing is part of learning. That's why I try to get right there in system. All right. So if you don't have any question, we probably gonna start review next Wednesday. There is a practice question set already on here. Can see test 4. That was a test 4. Basically, is parametric equation or polar equations. Most of them follow really closely to our homework question. So I don't have a lot of big deviation from this, so probably would be quite similar to this. And there's also a study guide about what kind of question I was planning on to do. There's a question where you can see for each question, you can almost identify a formula for it. Area within the polar curve, it's A1/2 theta squared d theta integration. Length of the curve is another integration. You can try to summarize what you really need for you to answer those questions. And the example basically is a copy of it. So I think that was the review. In the review, there should be solution already included. So test 4 practice question and solution is already online. All right, as far as today, I think I downloaded a 10.1 file, so I'm gonna continue. Unless you have any specific example, we'll talk about any question that you had over the homework, over the practice question, But if you don't have any question, I normally try to review the day before the exam. So next Wednesday, we'll try to talk about any question you have for test 4 or general solution for test 4 questions. Right. So today, we have time. So then let's talk a little bit more about this three-dimensional coordinate system that we started yesterday. So hopefully it makes sense. I mean, so basically three-dimensional coordinate system is one step forward from two-dimensional coordinate system. Because two-dimensional coordinate system is more limited to what you see on a piece of paper. And that's why two-dimensional coordinate system or representation of function and equation using two-dimensional coordinate is more visual and easier to understand as you do more graphing, as you see more example. But three-dimensional, that's why I recommend more people to learn a little bit about how to draw three-dimensional object, so you can see that perception of three-dimensional situation. So we would start representing a point using, instead of 2 point, we use instead of 2 number, we use 3 number as our coordinate system. We added one more value that's called a z coordinate. And then if you add one more number to it, you have to add one more number line to your coordinate system axis. So instead of x-axis, y-axis, now you have one more that we call the axis. So a typical thing to do is the x-axis and y-axis are horizontal, and the z-axis is vertical. So that's one way to set it up according to the right-hand rule we see in the image, or this way. So that's x, y, and z. They're supposed to be perpendicular to each other. So three number lines perpendicular to each other, starting at the same origin. And so about the coordinate system, we have to keep in mind the orientation is really important, because it's not this way, it's not opening down, it's opening up as you roll your right hand. I like to roll my hand across the crossing through the axis, and the thumb is pointing to the axis. All right, so and then we talk about how we draw our coordinate system in a three-dimensional view. So in the picture, you see 2, 1, 3. So you can put your x-axis horizontally, y-axis vertically, and z-axis horizontally out of paper, pointing out of paper. So that's one way, the one perspective, one point of view. In this case, to identify point 2, 1, 3, you can find the 2 on the x-axis. You want to find the 1 on the y-axis. And draw horizontal line, perpendicular line with the axis. So parallel to the axis, and then there's the vertical parallel to the y-axis. We have that point of 2, 1, 0. So from 2, 1, 0, we went. And from 2, 1, 0, we're going to go 3 units along the z-axis. So to make sure we do it right, we want to find the actual 3 on the z-axis. You see that, and these two are going to be parallel. So we kind of use parallel lines or parallel relation to identify distance and try to visualize what's going on. So that's one point of view. Another one is use horizontal x-axis and y-axis, but having the z-axis vertical. So this way, to identify the point 2, 1, 3, and then x equal to 2 is over here, y equal to 1 over here. So this is a 2, 1, 0. So from 2, 1, 0, you're going to go up 3 units. Actually, find the 3 units on the axis and parallel to that to identify exactly how much you go from 2, 1, 0 to 2, 1, 3. About the three-dimensional coordinate system, do you have any question? All right, so sometimes we may feel like we understand it, but if we truly understand it, we might see the differences when we see a question that was hard to do. I recommend having some three-dimensional graphing to play around and understand what was a three-dimensional coordinate system. For example, the one we were just doing is 2, 1, 3. So this is giving us a 0.213, and this you can play around and move your vector system. This is a vertical v-axis. The red one is the x-axis, and here I think the green one is the y-axis. So those points matching x equal to 2, right? And then y equal to 1. It's a little hard to tell whether the y is 1. So you would find 2, 1, that's 2, 1, 0, and you're gonna go up 3 to find 2, 1, 3. So right, so that's let's say it's from GeoGebra. GeoGebra means a combination of geometry and algebra. It's a graphing tool. So this is nothing in addition to decimals. Decimals can only draw a two-dimensional image. So if you were trying to look at things, graphing things in two-dimensional, normally most of them can be done with decimals.com. This is a GeoGebra graph with three-dimensional event. This is a three-dimensional calculator using GeoGebra. I was using this when I was teaching my geometry class. It was really useful. Anyway, so from that, just try to provide some more assistant tools when we don't have a lot of visualization. It's hard to understand the function or the image. All right, so yesterday we did talk about distance. So three-dimensional distance is different than two-dimensional distance. So if we have a point in a single plane, we have x value, y value, so x1, y1, x2, y2. The distance is x1 minus x1, x2 minus x1 squared plus y2 minus y1 squared and squared root. But three-dimensional distance, we have 3 coordinate x, y, z. And if you have 2 different points, you have x, y, z for the first point and x, y, z for the second point. The calculation of distance will be subtract their x value, y value, and z value, and find their summation of square of the deviation and square root of summation. So this was one of the examples. Given any 2 points, we should be able to find their distance. I think I assigned some homework on that, so we would know how the distance formula works. Is this. All right, so 2.1. I didn't assign a lot of homework, and this is a focus on the XYZ coordinate system. That's why I call it XYZ coordinate. This was the second question. This question is calculating the length of OR. So R is 5, 8, 10. O is the origin. The origin is 0, 0, 0. So the distance will be square root of 5 minus 0 is 5. So you have 5 squared. 8 minus 0 is 8. So 8 squared. And then 10 minus 0. So 10 squared. So that square root will be the final answer of this question. Anything else related to distance? Find the length of the side of the triangle with these 3 vertices. So this will be the kind of question you need to find the distance between AB, distance between BC, and distance between AC. So it's pure the distance calculation. So once you find the sides, the distance is AB, AC, and BC. Isosceles triangle is when all the sides are equal. So if they're all equal, that is isosceles triangle is when 2 sides are equal, right? Yeah. So if any of these 2 are equal, that is isosceles. If none of them are equal, that is what people call scaling. Scaling. Yes. Thank you. You have your geometry. So any questions? Thank you. All right, so with the distance formula, we will be able to start talking about distance from a given point. So we have this formula of it's not a circle anymore, it's a sphere. So in two-dimensional, we have the two-dimensional formula for a circle. It goes x minus h squared plus y minus k squared equal to r squared. That used to be the formula we had in college algebra, but now we added the coordinate to it. So the summation of square instead of 2 of these to add, and now you have the z minus c squared. The center is, when I was teaching algebra, I always use h and k for the center of the circle, but now we're using a b c in this book. Notation, which letter for the notation of the center is okay. So you can use HC or you can use HJK, but the idea is the x minus the center represent the distance. So we have the horizontal distance x minus a, vertical distance y minus b, z minus c is the distance in the z direction. So we added all the differences, square the differences, and that is the total distance. So it should be equal to r squared. It's actually square of the distance. Any question? The equation here really represents from any point. So let's say ABC is on a sphere on the outside of the ball. Then from this point X, Y, Z to the center ABC, the distance always equal to the radius. So that's really a square both side equation of a distance equation. So essentially equation of the sphere is really a simplified distance equation, a distance relation. Okay, that's why we will always define the distance formula and then define the surface of a sphere. Now, starting here, we start trying to find a way to represent all kind of different types of surface. And let's think about equation in 3 dimensions. If we have any equation in 2 dimensions, that equation represents a curve. It could be a line, it could be a curve, which means a line that's not straight. But in 3 dimensions, if you get a single equation, it represents a surface. But what kind of surface? That is the problem. And this section actually introduced many different kinds of surface. One of the special surface will be a sphere. A sphere has x squared, y squared, z squared. Coefficient of every square is 1. All right. So that brings out another question. What if we have x minus a squared plus 2 times b minus y minus b squared? So you get any of the coefficient of a square not equal to 1. And that will be something that will be a sphere being adjusted somehow, right? It will have either the y a little bit bigger or z a little bit bigger than the y. So that will be, instead of a ball, a circular ball, now we have a football, possibly. Something that has, like, what's that word? An olive or something. So it's a 3-dimensional figure similar to the relation between circle and ellipse. We got oval shapes, right? Something. So I think there's a term in calculus, we call that ellipsoid in comparison to a sphere. So we went over this example. If we have a sphere, equation of sphere, you could have this equation of sphere where the summation of square is clear. The center can be read in there A, B, C. You have variable minus the number square, variable minus number square added together. This is the one way people call this standard form of the sphere. You might have this that people call the general form of the sphere, where the ABC is not so clear. So when the ABC cannot be immediately seen in the equation of the sphere, we may have to complete the square. I went over this yesterday. Any question about completing the square? So basically what we did with +1 for the x plus 4 for the y plus 9 for the z. That way we were able to complete all the squares and have a equation of the summation of the square. In there, we can see the center is -1, 2, and 3, and the radius equal to 4. So after the equation being rewritten into a standard form, we now can see the center of the sphere and radius of the sphere. All right, let's go ahead and talk about some general surface. The number one most common kind of surface is something that's really, really flat, a plane. Right, so then there are a lot of different kinds of plane. The most common one is what we call axis plane. What you see here coordinate plane. These are all equation of the plane, but, this are the visualization of the plane, but we should really put a equation to them. I was gonna try to change it, but here we are. Let's talk about how we represent them. So for example, whenever we use an equation to represent a surface, we would wish to put equation. For example, this is an XY plane. XY plane is formed by spanning a x-axis and y-axis. So x-axis and y-axis are perpendicular. So they're forming the structure or the axis of this plane. And in that plane, you have different x value and y value, but every point in that plane has the same z value. Guess what's the z in the xy plane? Z equal to 0. So that is the equation we describe the equation. So for xy plane, you have to use an equation to represent it. It will be z equal to 0. I mean, I'm trying to use equation to represent any surface that we study. Because equation is really one of the main method which we calculate. This is the z equal to 0 point. All right, so the second one is the middle one, that is the YZ plane. Okay, so the YZ plane is formed by the y-axis and z-axis. Y-axis and z-axis are perpendicular. So they're in this YZ plane. We have y value and z value, which could be changing, could be variable z, variable y, but we have the same x value, right? So x equal to 0. So x equal to 0 will be the formula we were given to the YV plane. You can kind of see there is this same in relation to all the x, y, v value. In the YV plane, x equal to 0, just like on the two-dimensional case. On the x-axis, y always equal to 0. On the y-axis, x always equal to 0, right? We only have x, y coordinate. But now we have three-dimensional system. So now there's one more thing left. What do we have? Like an equation for the x-y plane. The equation will be the same equation. Y equals to 0. Okay, this brings out another thing about distance to a plane. And we had that question in the homework set. Maybe we should talk about it this one. Okay. And see, we were given 3 points A, B, C. The first question saying which one of these points is closest to a YZ plane. So now, if you want to study the distance from a point to a plane, you have to kind of know what is that plane special at. For example, the YZ plane should be represented by x equals 0, right? So on the YZ plane, x equals 0. So what was the distance from any point to the YZ plane? That distance is not related to the x or y, it's related only to its x value, right? So for example, the first point A, the distance from this point to the YZ plane is the x value. So it should be 8 units, because on the YZ plane, is x equal to 0. The whole plane is the x equal to 0. So from the x equal to 0 plane to 8, 13, negative 17, the y and z is, you have the same yz value in the yz plane. The only thing that actually matters is x value, right? Because that's the location of the yz plane. The yz plane says x equal to 0. So x value is how you pull out, how you calculate. So that's the one thing that's special about YV plane, right? So distance is 8. For B, the distance is 17. I mean, distance to the YV plane. Then the C, the distance will be 6. We're talking about distance. Distance will always be positive. So the one closest to YV plane is C, right? The distance is going to be number. So this one is C. Distance from the YV plane to this point is 6. So it's 8, 17, and 6. 6 is the closest. So let's try the second question. Which one is the furthest to the xy plane? So if we want to find how far any point to the xy plane, which point are we focused on? The z. Okay, so z. So let's look asking which z is biggest. Which one is? So we answer A. Okay. So we answer A and we put some D. So the distance is 17. Remember the distance can only be continuous. We take the absolute value of it. And that should be the first two. I assume that we should eyes on the x plane, which would be B, right? If it's on the xz plane, the y equals 0. This is the only one that y equals 0. Kind of. This is the question I mentioned the pointed plane. That's why I feel like that's kind of related to this example. Right, so this is some so those are the special planes, but there's not so special planes. So you can have a plane that's not exactly the YV plane, but a little further away from the YV plane. This is a plane x equal to 2. Right? So you can have a plane defined by a linear equation. But by linear equation, we mean what is linear equation? Linear equation is linear represent equation of line. Equation of line has degree 1. So as long as the variable is degree 1, that is the equation of a plane in this case. So in 3-dimension is now different from 2-dimension. If you remember when we studied calculus, x equal to 2 represent a vertical line, right? But now we have the 3-dimensional case, x equal to 2 is no longer a line, it is a plane. Plane representing all the points that has x equal to 2. So it's really 2 units away from the YZ plane. You see x equal to 2. A YZ plane has x equal to 0. Now we have x equal to 2. So the plane parallel to the YZ axis. But it's away from the factory. Any question? Right. I want to mention one more thing when we look at equation, different equation. These equations sometimes has x, y, z. Sometimes the equation do not, like this one. You have x equal to 2 is the equation of the plane. It doesn't have y, it doesn't have z, right? Right? So when the equation is mixing a variable, so this one does not have the y, which means for this, y can be any number. So for example, on the plane y equal to 2, you have the whole any y value or any z value, right? So it's free of y and free of z. Therefore, this one, x equal to 2 is the only requirement. So we don't, so the visualization or the picture of it or the plane itself is parallel to y and z. So that's the y-axis, this is the axis, the whole plane is parallel to the z-axis and it's also parallel to y-axis. So when the variable is missing, it represents geometrically, it represents a parallel relation with that particular axis. All right, so we're going to talk about this parallel relation again, but so numerically or algebraically, we have that variable removed, and as a consequence, geometrically, you see a parallel relation between the graph of this equation and the actual axis. Okay, this kind of shows the graph of the equation, the plane or the surface in its relation to a certain axis. All right, it's the equation of a linear equation representing a plane. The plane don't have to be exactly vertical or horizontal. Let me try to see a few more examples of a plane. Let's see that. And then, for example, we could have x plus y equal to 9. See this the one? So you can see this is the equation. Make it more visible. I'm writing the equation x plus y equal to 9. So in this equation, there's no z. So you're going to see if you only limit to 2-dimensional case, you're going to look at the xy plane to project it. Right, not really making the picture too small. So if you project this way, in the XY plane, that is a line, right? That's a line that says X plus Y equals 9. But when you look at, okay, I mean, when you rotate this, look at three dimension, it's a plane, and it's also a plane parallel to the axis. The equation does not have Z, so really the whole plane is parallel to that axis. So that's equation of a plane. So what if we have that one more axis? What do we have? Plus 2Z, right? Plus 2Z. So this is how it looks like. Right, so now it's not parallel to any axis anymore. You see something, a plane. It's still flat. The whole thing is flat because it's a plane. So it has intersection with axis, y-axis, and the axis. So it loses that. We no longer have that what people call parallel relation, right? So when we have x, y, x and y and z in the representation, in the equation representation of the surface in the plane, and we have intersection with the x value with the x-axis. That's when the y equal to 0, z equal to 0, x equals 3. So on the x-axis, the certain CF5, and then on the y-axis, when x is equal to 0, that's on the y-axis. On the y-axis, x equals 0, z equals 0, y equals 3. So on the y-axis, we see it's supposed to be 3. Anyway, on the z-axis, z equal to 3 over 2z equal to 3. So 3, z equal to 1.5. Yeah, really see much of detail. You can kind of adjust your point system to see the intersection. Okay, but this is just a three-dimensional view of the image. You have to adjust it to see better. Anyway, as a summary, an equation of degree 1 represents a plane. And let's talk about other surfaces. So number one surface I got to mention is a cylinder. And this is a cylinder, definition of cylinder. That is a little broader than our usual idea of cylinder. When we think about cylinder, we think about the cylindrical cylinder, where the base is a circle, the top is a circle, and you see a upright cylinder. But here, by definition, cylinder, we talk about you have to have a curve C. A curve C is a curve in a plane, and then you're going to have the direction of the cylinder. We call it L. L is a line not parallel to C. In a sense, for the most part, L and C could be perpendicular. So the L could be like this, right? And the C could be like this, right? So the C is being copied over and over along this L in that direction, right? And then, so here a cylinder is all the point on the line parallel to the L that passes through C. So you repeat the C in the L direction to form the cylinder. So curve C is being called the directress of the cylinder, and the lines are the ruling, or the L is the ruling. Any question? Okay, so basically we're saying cylinder can be all different shapes. Doesn't have to be circular cylinder. It could be circular cylinder. It could be elliptical cylinder. It could be parabolic cylinder. It could be hyperbola cylinder. And those terms talking about the C that's directing the curve in the cylinder. Are we okay? All right, so let's look at a couple examples. This is a circular cylinder where you have x squared plus y squared equal to 1. And you can see we have a ruling in this one. The direction of it is parallel to the axis. So in this case, you see x squared plus y squared equal to 1. In the xy plane, x squared plus y squared equal to 1 is a circle. So on the xy plane, you see a circle. But along the z-axis, this circle is like a parallel to having a lot of lines parallel to the z-axis, and we are going around the circle. that all those lines going around the circle forming that cylinder. So x squared plus y squared equal 1 is what we call the directress of the cylinder, and the rolling are the lines parallel to the z-axis. So this is a circular cylinder parallel to the z-axis. Any question? All right, this is why I keep talking about the rolling. Talk about the direction of the parallel relation to equation. Normally, the kind of cylinder we are doing are parallel to one of those axes, whichever variable that was missing tend to be the ruling, the parallel ruling of the cylinder. So this is a 1. And so you have to read the equation really well to know which direction the cylinder is. So this one, we see a cylinder that's parallel to the z-axis. You can also have x squared plus z squared equal to 1, which will be a cylinder parallel to the y direction, parallel to the y-axis. So we can see example cylinder. Once we get the idea, so you can see a cylinder it doesn't have to be one form. For example, we can go x squared plus y, well, we did y squared already, plus z squared equal to 4. So this is a cylinder. We should try to make this size smaller. Just enlarge this. This is a cylinder in the y direction. See, that was the cylinder. This is the x-axis horizontally, and the vertically is the z-axis. Right here in the y-axis is right in the center of the cylinder. It's parallel. This cylinder is parallel to the y-axis. You see the y value is not in here. Whenever a variable is not in the equation of the surface, that's a free variable. That means any y is okay. Well, in this case, is any z is okay. So we are parallel to z-axis. Any question? So we want to have some general idea about the possible form of cylinder. So a couple other examples. So this is a z equal to y squared. And whenever the variable 1 is squared, the other one is degree 1 and degree 2, they form a relation between the two variables, a parabolic relation, correct? Z equal to y squared. So then z is always positive, but y could be positive or negative. It's symmetrical about the z-axis, but keeping the z positive parallel, parabolic relation. The parabola, right? Okay, so, and then there's no x in here, so this is a parabolic cylinder parallel to the x-axis. And we can graph it, but graphing takes time. Instead, we'll just look at how it looks like visually. X equal to y squared. It's z equal to y squared. This is z equal to y squared. So this is what we call a parabolic cylinder. It's a cylinder because it's a parallel to the x-axis. This image, and then over here we also see x equal to sine z. So x equal to sine z, there's no y-axis. This x equal to sine z is a sine wave, but it's parallel to the y-axis. That is also a cylinder. Any question? This wave, it doesn't have a range determined, so it's going to go on and on and on. You're going to see kind of like a fabric going up and down the wave. The textbook did provide some assistance in the graphing. The z equal to y squared, if you only graph one curve within the yz plane, it looks like this. Then that's the directress. When I repeat this, there's a lot of ruling along it. And all these ruling you connected, they forming that surface. So that's a parabolic cylinder. And on this one, if you graph the sine wave, that's equal to sine z. Z would be the independent variable, x equal to the dependent variable. And along this direction, parallel to the y-axis, you draw many lines along the wave. and those lines forming the surface, that's a cylinder, a cylindrical sine wave. Any question? So, right, let's talk about other kind of surface. We're gonna try to provide some example on how to interpret those surface. So number one, let's talk about surface of revolution. By revolution, we mean with revolving a curve along a certain axis. So here we have an example. You take the y equal to root of x, which is a root function in the xy plane. In xy plane, you draw a root function, and now you could revolve this about x-axis. So here is our x-axis of the revolution. Right? We have a curve revolved. We did that. We did calculate surface area, which curve is revolved about a certain axis, certain rotation center. We're forming a three-dimensional surface. It's not flat. So here we're not calculating surface area, but we're putting on a three-dimensional equation to represent that surface. So y equal to root of x is a two-dimensional curve within the xy plane. But after we revolve it about x-axis, it's forming a three-dimensional surface. So we wish to have an equation to represent that surface. So how do we represent it? Once you're revolving a curve about the x-axis, this rotation, it has a radius a equal to y squared plus z squared. I mean, you can see the picture here. If you start rotating it, the distance from the center to the edge will be the x value, the y value square plus the z value square. Because the x value is perpendicular to this plane, to the circle. So when you try to calculate the radius, it only correlated to the y value in this direction, the value in this direction. So the whole distance is the point have the x value and the z value. So it's x squared plus y squared equal to r squared. That is caused by this equation. R squared equal to y squared plus z squared is a Pythagorean relation, but it's from a three-dimensional rotation. Okay? And then in the two-dimensional case, if you rotate y equal to root of x about x-axis, the radius equal to y value. If it's equal to y value, then equal to root of x. So r equal to root of x in the two-dimensional case. So when we compare this to, then the r squared equal to x, y squared plus z squared equal to r squared, therefore a equal to x. That's the last equation is the actual equation of this surface of revolution, like this. We try to explain a little bit better. The two-dimensional equation is y equal to x squared. Okay, so this is a two-dimensional picture. If we rotate about x-axis, then the rotation center equal to the radius equal to y. This is a vertical line parallel to the y-axis, right? The radius equal to y, and y equal to root of x. So that means r actually equal to root of x, right? And then the three-dimensional case. So in two-dimensional, radius equal to y equal to root of x. But in the three-dimensional case, since the rotation radius only related to the point, the y value and x, and y value and z value for that point. So y squared plus z squared equal to the r squared in the three-dimensional rotation. So you can see the differences when you are thinking about the function in two-dimensional scenario compared to what it is in the three-dimensional scenario. And then these two supposed to set equal to each other. So this r is that r, and then the r equal to y, therefore equal to root of x. So this r equal to root of x. So these two equations are really the key connection between the two-dimensional case and three-dimensional case. Originally, y equal to root of x is a two-dimensional equation. After the rotation, we're able to form a three-dimensional surface. So within these two, square both side equation of r equal to root of x, we have the r squared equal to x. So finally, we have that surface. This three-dimensional surface is y squared plus z squared equal to x. We can actually see how it works because in the original equation, you have y equal to root of x. This is a y, and that is a x. I draw it with a blue curve. In the three-dimensional case, you see that that's the same x, and you have the same x on the x-axis. And then when you rotate it, this is a y, right, in that picture. But after your rotation, remember you have to maintain the r. It's this. So this one is a y squared plus z squared for that point. But of course, this one, this is a y in that root of x there. So you can see because of circle, this equal to this, and that is the x, this is the root of the x there. So everything still fits, even though they're different, like two different, compared to a two-dimensional case with the three-dimensional case. I hope that was okay. Any questions?
Have you ever done any computer aided design?
No? Why do you ask?
Oh, it's because most of it is in a community plan.
I see. Okay, so, I mean, this part, the textbook provided a solution, which pretty much is this. So when I was start looking at it, I felt like the explanation was a little brief. So I was trying to think about how we kind of connect it. The textbook already had the image using computer. This is the two-dimensional cases in the XY plane, and we're just try to rotate it to see how it related to the three-dimensional case. Maybe you guys have a quicker connection, but when I'm looking at it, I don't see the connection. So I decided to separate the two-dimensional case with the three-dimensional case. I'm hoping it was not too hard to understand. Any question? Are you okay? Or are you completely confused? Do you have any questions? All right, we do have some like rules or something we can observe. So from that example, we're gonna try to generate a plan for how do we handle this kind of question. It's really not the focus of chapter 10, but being able to think about this allow us to connect many of the equation. I mean, one of the question in the homework is to identify this equation represent what kind of surface. Some of the surface are like a revolution. So you can see it's rounded and circular and symmetrical. Some of them are not, but being able to see that that is a surface revolution, that is not, which probably will provide better understanding of the equation itself. So this is your creation of the equation, but when we look at our homework, we see equation that's already there. The question is, what kind of surface that equation, what kind of surface that equation. So if we know the source of how the equation is being created, maybe we have a better understanding of them. So anyway, these are talking about your rotation and to dictate how you write your equation. So if you have an equation in the xy plane, y equal to rx, which is what we just did, and you're rotating about the x-axis, right? Notice that x is a independent variable. You're rotating about the x-axis, and as a consequence, the radius is y squared plus z squared. So your formula y squared plus z squared equal to r squared, and r squared already in your original formula for y rx. So similar idea. If you have x equal to a formula of y, and somehow you rotate about y-axis, notice the y-axis is the independent variable over here. So whenever we rotate about the independent variable, it's in three-dimensional case, we have rotating about y-axis, the radius equal to x squared plus z squared, and also that means we are x and z both are perpendicular to the y-axis. So then our radius is being represented with a y formula, which will work out. And then last case is if you have x equal to rz, where z is an independent variable, then in that case, if you're rotating about the axis and the r squared equal to x squared plus y squared, and which equal to the radius representing using the z variable. So this will work out if we have that the rotation center being the independent variable of the equation. I hope that was okay. All right, there's a couple examples here. The first example is rotating y equal to sine z from 0 to 2 pi. We're rotating it about the z-axis. Again, z is an independent variable. If you rotate about independent variable axis, then you have the radius equal to x squared plus y squared, which then equal to sine z squared. So think about the reasoning here. In two-dimensional, whenever you rotate about the axis, your radius always equal to x squared plus y squared. In the two-dimensional case, if y equal to sine z, if we draw the picture, we can view in time, right? And then the radius will equal the y value, and the y value equal to sine v, which then means r equal to sine v. So that provides a relation of the r value, and then compare this to replacing the r with this formula. We would have x squared plus y squared equal to sine v squared. Right, that echo what we have in that key idea page in question. Right, so once we practice a little more, we kind of see some pattern. This is the formula for the x squared plus y squared equal to sine v squared. One we just did. So you see something that was really revolving the sine v curve about the z-axis, it's forming that surface there. And another question, well, that was the answer to the question. All right, so then there will be another different question. What if we don't rotate about the independent variable axis? For example, z and x. If we rotate about x-axis, everything will be fine, which will be y squared plus z squared equal to f of x squared. But now, what if we rotate about the z-axis, right? What if we rotate about the dependent variable, the outside, the z? Then we have a little bit of problem, because if you rotate about the axis, right, and then r squared will equal to x squared plus y squared, but then the x is over there, so we have a confliction of variables, and there's a problem. So then what we're gonna do is actually having the r equal to root of x squared plus y squared plug into the x, this x there, because if you rotate about the axis, in the xz plane, your radius is the x, is the x and the opposite variable. So we will replace the x value by the radius itself. So that was the method. So whatever is your rotation center, that is the one that you have to substitute. So in this case, we substitute the x there, because that's the radius, x is the radius if we rotate about the axis. All right, so let's look at example to see how it makes sense. So this is a question. We have equal to sine x. We want to rotate it about the axis. So again, in three-dimensional view, if you rotate about the axis, then automatically you have x squared plus y squared equal to r squared. That is part of the equation then. And then this equation, let's look at the two-dimensional picture. Z equal to sine v. We would draw it on the xz plane. Here is our x, and that is the z. So if we rotate about the axis in the two-dimensional case, this is the radius equal to x, which means that x equal to the radius. That means this radius replace the x. So the substitution looks like this. The inside is being substituted because the inside is x equal to the r is the root of x squared plus y squared. So we actually substitute x for root of x squared plus y squared. Example rotation. After the rotation, this x is a two-dimensional x. This is a three-dimensional that we did. So, any question? So we're taking this 1, 2, 3 and combine them into the equal to sine of root of x squared plus y squared. So that's three equations combined into one equation. It's the three-dimensional image. So that would be the answer to this question. And we can actually see how it looks like. This is a picture provided by the textbook. And you can also draw it yourself to see how three-dimensional view of this. So that's v plus sine square root x squared plus y squared. So it's really the sine wave rotated. So you get a sine wave and you rotate it over and over. The thing about this, think about this curve. It's a sine wave. You rotate the whole thing, which will end up giving you something like this wave surface. Okay. So that is a revolution about the axis of the sine curve. All right. So let's make it more general. One of the homework question is being able to identify the surface This is a general definition. Any degree 2 equation in three variable are being called, the equation represent what we call quadratic surface. Quadratic because we have degree 2, x squared is degree 2, y squared is degree 2, z squared is degree 2, x times y is also degree 2, and then we have x, y, z, those are degree 1, and then the number j is degree 0. We do not have exponential function, logarithm function, or any trig function. So the equation is purely degree 2 or lower polynomial of any variable. So this is called quadratic surface. So I'm going to try to look at a couple of scenario of quadratic surface. For example, what if let's say all the combination variable equal to 0 is being there, then we probably need time to complete the square. But let's say we're just having a squared plus b squared plus c squared, and those a, b, c are going to give us some combination. Let's look at a couple examples. Start with this one. This is what people call elliptic paraboloid. So the equation is z equal to x squared over 4 plus y squared. The image is right there. So let's think about the relation between the variables. Number one, relation between x and y. We have x squared plus 4 equal to y squared, x squared plus 4 plus y squared. Let's say z equal to a number. I mean, in this case, z can be 5, they could be 1, or they could be 2. But for any z value, x squared over 4 plus y squared, let's say equal to 1, it will be like over here, z equal to 1. So it's an ellipse with a 1 in the equation, right? If x squared over 4 plus y squared equal to 4, so it's going to be a higher elliptical curve. So that's why the name is called elliptic. So there is an elliptic curve in the image of the equation in the question. And it's also ellipse equation whenever z takes on any number, right? Z equal to 1, z equal to 2, and then you are forming the equation of ellipse. So then basically relation between the variable x and y is ellipse relation. Right, and let's talk about other variable, relation between z and x. So assuming that y equal to 1, I mean, y is a variable takes on value. If y equal to 1, it's like here, slicing it over here, slicing at y equal to 1. Y equal to 1 is a plane. So like having a plane cutting the surface at y equal to 1. The cross section will be z equal to x squared over 4 plus 1. Which will be a parabola. Same thing with with x, z, and y. So between z and y, z equal to, I mean, x will be number 1, x will be 2. So z equal to a number plus y squared. So z and y squared, when one of the variables squared, the other one is degree 1, is a parabola, right? It's parabola in the yz plane. So basically speaking, this is why the name is called elliptic paraboloid, because there are one pair of elliptical relation, x and y, x variable and y variable is elliptical relation. And then there are two pair of parabolical relation. So if you think about z and x, z is equal to x over 4, z and x is parabolic. And then z equal to a number plus y squared, so z and y is also parabolic. So that is where the name ended as a paraboloid. The three-dimensional term, the surface. Any question? We okay? So that basically saying if you have two variables square added together, it's elliptical, and then one variable is degree 1. So compared between the two variables is a parabolic relation. So then we have this general form of formula for elliptical paraboloid. That's whenever, here's more general, a and b could be any number. The earlier page showing a equal to 2 and b equal to 1. So a the denominator a and can be any number. Now this is a elliptical paraboloid in the z direction, so it's open to z. But it doesn't have to be this way. It could also be x equal to z squared plus 2y squared. So it could be x being the single variable on the left side equation. So you can have a elliptical paraboloid opening this way or opening that way. So it doesn't have to be z, x, y. It could be y, z, x. So the variable can be rotated, so then the surface can switch direction. Right, so that's the first special case. So basically, if you relate to that one, that's kind of like two of these stay as square, and that one equal to 0, and then one of these variable equal to 1. Right, so then a couple of maybe A, B, C, one of them equal to 0, maybe G and H, one of them is -1. So that's the elliptical paraboloid. Let's move on to this one. All right, this is slightly different from the earlier example. You see here, you have z in degree 1 on the left side. Now, what if z equal to degree 2? And then, so the picture also are related and yet not related. If z is a square, right now, z is degree 1, which means a summation square equal to z, that means z has to be positive, right? Adding two positive, z is forced to be positive, so z is up. But what if you have z squared there? In that case, z can be negative or positive. So the image of this is called elliptical, because z squared equal to x squared over a number plus y squared over another number. In this case, z can be positive or negative. You see upside down cone there. All right, so what kind of relation do we see here? Of course, when z being any number, z squared is a positive number on the left side. So you have x squared over a number plus y squared over a number equal to a positive number. So between x and y, we still have elliptical relation. I mean, x squared over 4 plus y squared over 9 equal to 1 is an ellipse. So we see elliptical relation between the x variable and y variable. But on the other hand, what is the relation between z and x? It depends. If y equal to 0, then z squared equal to x squared over d squared. Simplify is z equal to x over d. So you have a straight line. Okay, so whenever you go through the origin, you see a straight line, which is on the side of the cone, right? And another thing is, what if y is not 0? If y is not 0, see y equal to 1. Right, we're going through the cone in a non like y equal to maybe a y equal to 1. In your slicing the cone at y equal to 1, right? So you end up having what I think is a hyperbolic relation. I think we talked about the cross section. Now we have a cone, right? It's like a different way to slice a cone. But anyway, this is a cone. In the cone, you will see ellipse, you see hyperbolic, you see parabolic, depending on whatever way you slice the cone. Any question? And so anyways, going through the origin, we see straight line. So I see the side of the cone. That's this example. So very similar, but this one had two square variable, one degree 2, degree 1 variable. And this one have all three variables squared, but they have equality, right? And this one is called ellipsoid. This is when we see elliptical relation between x and y, between y and z. So it's elliptical relation between any two pair of variables. So v equal to 1, right? That's a number. So it's elliptical relation. It's an ellipse with x variable and y variable. If x equal to 0, you see an ellipse with y and z variable. If y equal to 0, you see the elliptical relation between x and z. So it's overall, no matter how you slice the whole thing, the whole surface is always ellipse. Any questions? Are you okay? So that kind of gives you the idea. If it's x squared plus y squared plus z squared, you see a closed surface. And then if the ABC, if A equal to B equal to C, then you see a sphere. So in a sense, sphere is a special ellipsoid. It's when all coefficient of the square equal to 1. Basically, ellipsoid represent a curve where x squared plus y squared plus z squared having different coefficients. But when x squared, y squared, z squared are added and having the same coefficient, we actually see a sphere. So sphere is part of this special curve, special surface. Any question? Right, let's see. Almost done. This is a hyperboloid. Hyperboloid having hyperbolic relation between two pairs of variables. This is a hyperboloid of one sheet. Because there, you have two positive square, minus another square, you put a positive number. Another example would be, one positive square, subtract the other two square, you put a positive number. It's forcing the surface become two separate parts. That's a hyperboloid of two sheets. You kind of see the equation, the difference in the equation forces the graph, the surface take on different shapes. Any question? All right, I think there's one more. It's called hyperbolic paraboloid. That is when we have a hyperbolic relation between two variables, x and y are hyperbolic. Subtraction of square force hyperbolic relation between the variable. But then the third variable is degree 1. These two squares subtracted, that one is degree 1. So we have a parabolic relation between v and x. Have a parabolic relation between v and y. There's one pair of hyperbolic relation, two pair parabolic relation. We call a paraboloid, but it's not hyperbolic paraboloid. And this is something very special. See, we see a saddle, sometimes we call it saddle point. And that's all the special surface that we see in this section. And that's it for today. Hope that we get ready. So we'll see you Monday. Please bring your question and try to finish your homework. Okay. Those are the charts for
She's